Okay, so in this part, we are going to look at what is a root mean square speed and basically how we assign that number. You remember in the simulation just now on the upper left-hand corner, there are certain numbers like, oh, the gas is traveling at 400 plus minus meter per second. And then you notice that there's a speed distribution. So we kind of like need to have a method to deal with different values of particles speed, because when you think about it, since all particles travel in random haphazard motion, and if I to stick a ticker timer or do a light gate on all the particle, GG lo, I need to go home already because there are millions, billions of particles. So we need to use a very powerful mathematic tool called statistics. So since gas molecule exists in last number, we have to consider average behavior. So think about the gas particle. They are traveling in 3 dimensions. So let's say you have a gas particle, and I'm just going to resolve the 3 dimension into Vx, Vy, and Vz. Okay, and if I were to write this in a relationship using vector, after resolving, I can say that Vx square plus Vy square is equal to V square. Just like if you have x and y alone, you use Pythagoras, right? The same thing can be translated into 3 dimension. All right. However, for large number of particles, okay, so you can see we are continuing. For a large number of particles, we have to take average. So this is a kind reminder to you that for your root mean square topic, for this chapter, we use this arrow bracket to represent mean. In maths, they use the bar. Remember the bar X? You don't go and bar this one,
Yes.
because bar.
Got the V bar like that one.
So in
But we do
CIE
like this.
A level, we do the bracket, you don't confusion, you mean the same thing, okay? It means average. So for large number, I can just take average for all 3, right? So let's continue. So I write down here for you lah. Mean X is, and then since the gas particle is moving randomly, I can say the average in the X, Y, Z direction should be the same. Okay, just like if let's say I take a random sample of a quality A level student, they should have the same average bio, physics, and chemistry score lah. Cause quality A level student ma. So this is a quality ideal gas particle. So if I take a sample of ideal A level student, their average bio, physics, and math score should be the same. Ideal. Okay. So if they are all equal, then I can substitute or Vx into all 3. So now Vx plus Vx plus Vx is 3Vx square. Okay. And why are we doing this, miss? Okay, you see later, you will see how. All will be revealed. So let's continue.
Okay.
So I'm just going to write down the notation here where, okay, where whenever you see that mean arrow and a square, that means mean square x. So this is mean square speed because V is speed. All right. Notice the way I write the speed looks a bit weird. I put a curl like a year for this V because there's volume, there's gas particle speed. I accidentally go and cancel them, then I will go back and cry. I will go back and cry in physics. Stand in the corner and start crying. So you better make sure when you write these 2 things, they don't look the same for you. Okay? So I write it this way. I decide how you want to write. Okay? So that would be the mean square speed and how we treat. So right now, if let's say we have a particle traveling in the x direction, we can assume that if I take the average of that x direction is 1/3 the average of the total speed. That's the takeaway. We will continue to the next part. In this next section, I'm going to talk to you, or Miss Ellie and I will talk to you about how to derive the relationship between the particle that you're seeing here, they're just traveling back and forth in the box, and also gas pressure. So if you observe this particle, you will notice that it is colliding against the wall of the container. So for so many years, you have written as a science student that what causes gas pressure is the collision between the particle and the walls of the container. But why is that so? So here we are now going to derive or actually find the relationship between the speed of this blue color thing and the gas pressure. So I think I want you to look at a few things first. Notice that we have selected a particle, okay, that is traveling in the Vx direction, number 1. Number 2, notice that the collision time is really short. Look at this, very short. So as it collides and changes direction, the particle will exert a force on the wall. So I want you to hold this animation in your head while we move on to the next derivation. So why did we look into the group mean square speed or the mean square speed? Is because we are trying very hard to relate. If you remember the very first beginning of ideal gas, when Miss Ellie talked to you about macroscopic, the big things you can measure, and microscopic, the small thing that we theorize and we want to relate them. You know why? Because for years and years, all the science teacher tell you, nah, the gas particle collide with the wall of the container, creating gas pressure. And then you also, then you write all during the exam, and then you write so many times already. You have reached a point where you are ready for us to derive to you how this boing, this collision can give you gas pressure. Okay, first, let's consider a gas particle inside the container. So this gas particle, okay, I don't know why it's not appearing in the cube. It will appear in your own notes. So the gas particle will be on one side of the container, there, and then it will collide with the other wall. So we only take the x direction because remember previously, like a few minutes ago, we have derived a relationship between Vx and mean square speed. And the reason why we want to only use the x direction is because, ladies and gentlemen, momentum and forces are vectors. If you want to do this thing in 3D, we need to use matrices, and it's way beyond my pay grade. That one need to ask for further maths teacher, not me. So we will just stick to one direction. Yes. So the particle m is going to travel towards the ball and then hit the wall, okay, with the same velocity Vx, because all the collision is elastic. So it's going to now rebound or travel in the opposite direction, okay? And this rebound time is actually quite negligible at negative Vx. So the rebound speed is the same because, remember one of our assumptions, all the collisions has to be elastic. All right. So sometimes the past year question will actually ask you, what are the assumptions that are being made in this scenario? So of course, if this is the case, if you hit the wall at Vx and you rebound from the wall at Vx, you didn't lose any kinetic energy. All right. So let's continue. Okay. So from here, flip direction, so this is negative law. I will take right as positive, left as negative. Okay. And then, so you can see now, magically, it has appeared, and your particle will hit the same wall it originated from with the same speed, negative Vx. So the particle goes and come back. Okay? So right now, this collision here, at this point, because there's a change in momentum, let's say here t is equal to 0, there's a change in momentum. So there's a force that the wall exerts on the particle. And there's also a force where the particle exerts on the wall, which is what causes your gas pressure. So because we need to find force, so we need to find the change in momentum over time. So I'm going to need some time symbols here. So I'm going to start timing at time equal to 0 here. By the time it U-turn back, it will be time t equal to t. So this is time taken for the momentum to change from positive Vx, the blue arrow, to negative mvx, the pink arrow. All right. So the time taken for the momentum to change will be equal to the time for the particle to travel forward and then backward, because we assume that the collision time is negligible. All right. Okay, so you can see the collision time is negligible. So basically, the time where this particle is touching the wall is very, very short compared to the time for the particle to go back, go here and come back. Now this, I understand this is totally different than how you used to do a normal tennis ball hitting a wall. You actually go and measure the time the tennis ball deform and then rebound back. Remember in your AS? But you know, ideal gas, they are very hard spheres. They do not deform. So this collision time is just not there. So the only time that we can take that is meaningful is the time taken for it to go from positive Vx at the wall and negative Vx at the same wall. Okay, so I know it's a bit of a jump, but yeah, that's the basic idea around it. So again, two ideas. We collide, the momentum changes from Vx, mvx to negative mvx, meaning your total change is 2 mvx. To find the force, we are going to take this mvx divided by the time taken. All right, so as mentioned just now, when the gas particle collides with the wall and it rebounds, we are considering this gas particle and we assume that it has a mass m. Okay, I will keep reminding you that this lowercase m is the mass of a gas particle. All right, so if you want to find the change in momentum of the gas particle, we will take mvx, which is the initial momentum, minus the final momentum. So I think we write that one first. Change in momentum P is equal to change in negative mvx minus mvx. Because if you look here, your final momentum is negative mvx. Your initial momentum is vx. So minus initial minus final. All right. So this will be negative 2 mvx. Or you use logic lah, from positive 1 to negative 1. You change how much? 2. Okay. So this one will be equal to negative 2. And we are going to think about Newton's third law because this is change in momentum of the gas. But what causes the pressure of gas pushing out against the walls of the container is the force that is exerted on the wall. So the pressure will be F over A, which is the change in momentum over time. So del P over T A. All right. So we need to think a little bit about what that time is. Okay, because from Newton's third law, we know that the change in momentum of the gas particle will be the same as the change in momentum of the wall. So we can substitute delta P as 2 mvx. Okay, so the delta P can be 2 mvx. And at the same time, when you want to think about T, right, as mentioned just now, we are not actually taking the exact collision time for two reasons. Number one, too short. Number two, there is almost no collision time. The gas particles are very, very hard. So this will be, more than snooker balls actually. So this is 2 mvx. Just say you travel here with a speed vx, go to one end, come back with a speed negative vx. So, Miss, can I use the equation that you forbid us to use? Speed is distance over time. This one can, because the speed is constant. No acceleration. Can. Special situation. Don't get used to it. Do not use V is S over T in simple harmonic motion. I will strangle people. You laugh, Miss Ellie.
Speed is distance over time.
Distance over time. So we want to substitute T. We rearrange. Will be 2L over Vx. Poke inside. Bing, bang, boom. 2L over Vx. Do some preliminary cancellation. We go cancel a bit. Vx and Vx cannot cancel. Cannot. You cancel it's like the speed does not affect the pressure. And then nani? We need to rebrain our idea of gases. So we're gonna, before we simplify, the A we can substitute. A is the area of the pink face of my cube. Since this is a cube, so it will be L square. Okay, the area is L square. So we're gonna just put it inside the equation. This is L square. Now we simplify. The 2 can cancel out. Okay, and then Vx will be mvx square over L power 3. L power 3 of a cube. Is this not the volume?
Correct.
Yes. So we're going to put mvx square over capital V for volume. My friend,
this one way, you must make sure you don't confuse the V.
If you confuse yourself, I cannot help you already at this point. Just write differently, okay? How you want to write up to you. Make sure that you know that they are different. Okay? But this is for one particle. We only took one. Entire gas got many particle. What to do? Aiyo.
So all the gas, all bing bang bang, all each of them have changed in momentum, each of them exert a force. So times the number of particles, probably
can, but we need to, instead of taking Vx, we need to take average of Vx. So for n particles, so we need to first mention to remind ourselves, okay, now this is for 1, now we're going to do for n particles. All right, so for n particles, pressure will be n multiplied by mvx, but this Vx now will have to be the average of Vx. So we're going to put that arrow, that funny bracket, what do you call this, V bracket? Okay, divide by the volume. Aiyo. So congratulations, you have related the speed to pressure. But we need to do a little bit of treatment first. Vx is the horizontal direction. Unless you create a magical gas sample where all the gas travel in the horizontal direction, I cannot use the equation. So I need to
Supposed to be
include,
3D.
yes, the root mean square speed. So if we look here, the root mean square speed, Vx square is 1/3 of the root of the mean square speed. Okay, Vx square is 1/3 of the mean square speed. So we are going to plug it in right now. This will be m 1/3 of v square. Divide by big V. Okay lah, we 整理 organize a bit. Take the 1/3 out.
Yeah, Miss can bring V to the other side also, huh?
Oh, can. But you see, they are
PV? Like that?
can. So this equation actually exists in several forms. I will show you the form that exists inside your formula sheet, your favorite piece of paper. Okay or not? So this one, we keep one side. Sometimes this is useful, especially if we are comparing with the macroscopic equation. Because macroscopic, you have PV is nRT ma. Microscopic, you have PV is equal to half nm v square. This is mean square speed. So let us remind ourselves. N is the number of particle. Capital N is the number of particle. Small m is the mass of one particle. Miss, if I take the number of particle multiply by the mass of one particle, do I get the mass of the entire sample?
I guess we could do that. One
Yeah.
particle multiply by how many you have.
Yeah, so you get the mass of the entire sample. So then if I continue this, or if you can find space to squeeze it in,
Down here. Okay,
can. So I will need to bring the V back because I want to include density. So this will be 1/3. Nm is the mass of the sample. V is the volume of the sample. Okay, and then this will be still mean square speed. So this Nm over V is equal to density, rho. 1/3 rho V square. And sometimes your syllabus or your formula sheet calls it 1/3 rho C square.
Wow, why they use C? Why so different?
Sometimes they use C, sometimes they use V. They tend to use C more than they use V in this context. But then if it's in the half mv square one, I don't know lah, they're not consistent one lah, okay? So formula sheet is given, but formula sheet write like this way, 1/3 rho C square. They mean the same thing. The mean square speed, okay? So this, if you stare at this equation, now you know how they found those 400 something, 700 something, average or mean speed of your gas particle, because we can measure the pressure using a Borden gauge or a pressure gauge. Density can calculate, measure the mass, measure the volume. So from here, just using this basic equation, we can find the mean square speed. So don't forget these two useful equations in the box. And in the next video, we will carry on to try to relate. Okay, we know that, so what are the main ideas? In this main idea, we know that the collision causes change in momentum. And due to the change in momentum, there's a certain force. And because of that force, we get pressure. So putting all the mathematical treatment into all these statements, we arrive at this equation. PV is equal to 1, and also some statistical treatment. PV is equal to 1/3 nmv square. All right. So very foreign formula. We need to do some examples to get used to it. How to use it. Be very aware. The question like to trick you one. They will give you this equation in the question. Very nice, Miss. They give the second one, the formula sheet. They give this one in the question. So nice. Very happy, right? They go and give you the mass of the sample. 20 gram of gas. And then you GG or you go and put 20 gram there. You've forgotten. It's supposed to be mass of one particle.
One particle.
So you need to use the mole concept to find the mass of one particle. All right. Then once we got this, we have successfully related the macroscopic, which is pressure and density, to the microscopic, which is the mean square speed. From here, we can tell the faster the air particle, the higher the air pressure. Makes sense, right? More collision. That's what we keep telling you. More collision, higher pressure. More collision, higher pressure. Okay lah, can see already. If you move faster, you collide more. You collide more, you got more pressure. All right. But what is the second observation in the very first intro video? When you move faster, it's due to an increase in temperature. So in the next video, we are going to now pull this equation, PV is 1 over third and mv square, and relate and find a way to magic out a temperature into our equation. So I guess we'll see you in that video then. Bye.